Hello, this is Dr. Strickland. In this video, we're going to continue our investigation of chemical evidence by talking about how to identify the 5 different types of chemical reactions. So take a look at this. We've got a chart up here that gives you a description of each one and then an example. So we're going to see if we can't use our examples to help with how one would identify these things. Okay, so in a synthesis reaction, 2 or more reactants combine to make one product. So the big thing to identify is that there's one product. In a decomposition reaction, and there are a lot of decomposition reactions when you're talking about recovering of dead bodies or dead animals or dead plant matter. But in a decomposition reaction, one reactant breaks down into two or more products. So for example, in the decomposition of carbonic acid, there's one reactant. So I think those are, that's my main signpost for synthesis reactions and decomposition reactions. Now, there are a couple of different metathesis reactions that I want you to know about. You may know them as double displacement reactions. So in any metathesis reaction, 2 pieces of the reactants basically switch places. The ones I want you to know about are precipitation reactions and neutralization reactions. So in a precipitation reactions, the reactants are 2 ionic compounds that swap cations. So look at your reactants. Here we've got both of these guys are, a metal and a nonmetal. So that's ionic. Now we've got a metal and a polyatomic anion. That's ionic. So how do they switch cations? Well, the sodium cation is going to go with the nitrate anion in one product, and the silver ion is going to go with the chloride ion in the other product. But one of the products is a solid that doesn't dissolve in the reaction mixture, and that's formally the precipitate. Precipitate is an insoluble solid product. Let's try it again. If you watch the reaction, you would see that as the reaction went on, you would see more and more solid in your reaction mixture. Because at first there wouldn't be any solid at all, because see, these are both AQ. They're aqueous solutions, so they would just look clear, right? There would be no solid, no cloudiness, no solid at the bottom. But in a very short time, as the reaction converts the reactants to products, a solid would be formed, and you would see that. All right, so in a neutralization reaction, you've got an acid plus a base that makes a salt plus water. And a salt is an ionic compound. And there are 2 qualifiers. The cation cannot be the hydrogen cation, because otherwise it would be an acid. And the anion cannot be the hydroxide anode, because then you would have a base. But we'll talk about those down the road. But so we've got an acid plus a base gives a salt plus water. And sodium chloride, table salt, is the most famous salt, but salt is really just a classification. So it's the same kind of swap, though. The hydrogen atom in the acid swaps places with the metal cation in the base. So up here, it was 2 cations that switch places. Here is the hydrogen cation and a metal cation that switch places. So that you form sodium chloride from this cation with that anion, and water from this cation with that anion, okay? So an acid plus a base gives a salt plus water. That's what I look for here. And in a precipitation reaction, what I look for is the insoluble solid product. All right. A redox reaction is a single displacement reaction. And these would be much more difficult for you to identify. The only kind that I want you to be able to do are if you have a metal plus an acid. This is hydrochloric acid. It's the acid that's in your stomach helping to digest your food as we speak. And so I would want you to know that this is hydrochloric acid, and we'll talk about some other acids down the road. But so iron metal with hydrochloric acid makes iron 2 chloride, because iron is one of those metal elements that can form more than one cation. And then the other product is going to be hydrogen gas, because hydrogen is one of those diatomic elements. Okay, so I would expect you to be able to recognize this as a single displacement reaction, but I'm not going to ask you to know anything about the relative reactivities of metals or of halogens. Well, that's, that's above our pay grade at the moment. Now, in the other redox reaction type I want you to know is combustion. And we're just talking about burning, right? It's the reaction of something with oxygen gas in the presence of a spark or flame. Like methane is the major component of natural gas. And so natural gas reacts with oxygen, and the spark or flame may or may not show above the arrow, but it's there because the reaction won't happen in most cases without it. But there are some caveats to that. So you can put it above there, but if you don't see it above there, don't let that worry you. But the products are going to be carbon dioxide and water. There are other compounds that can do combustion, but the ones that I want you to know about are the ones that just have carbon and hydrogen in them. And so because of that, they're called hydrocarbons. Gasoline fits here, diesel fuel, candle wax, anything that contains just carbons and hydrogens is called a hydrocarbon. Okay, so I do expect you to know that much about being able to classify reactions by looking at a balanced equation. All right, so let's turn the corner and start to talk about moles. Now, I'm going to pull down this equation. We talked about how the coefficients in a balanced equation tell you the number of little things that react, like one atom plus two molecules gives you one formula unit plus one molecule. Those numbers also tell you about moles, because a mole is just a way of counting things, like a term's dozen or score or gross or ream. It's just that a mole is a lot of things. If you know Avogadro's number, 1 mole of something, 1 mole, let's just put 1 mole of objects equals 6.02 times 10 to the 23rd of them. So just like a dozen eggs is 12 eggs, and a score of years is 20 years, or a gross of pencils is a dozen, that's 144, or a ream of paper, that's 500 sheets. A mole is 6.02 times 10 to the 23rd. Now that's a really big number. So generally you only use it to count really little things like atoms or molecules or ions. You could count kangaroos or dump trucks by the mole if you wanted to, but it would be a lot of it. And so generally we don't. But when you're talking about a chemical equation, you can read this on the mole scale. 1 mole of iron plus 2 moles of hydrochloric acid gives you 1 mole of iron 2 chloride plus 1 mole of hydrogen gas. So it's a difference between the macro scale in moles and the micro scale in individual atoms and molecules and formula units. All right, so the molar mass is the mass of 1 mole of the atoms of that pure substance. All right, so let's talk about the chemical formulas of these things. Lead is an element, but it's not a diatomic element. So it has the symbol Pb. Now oxygen, that is a diatomic element. So we're talking about O2. And zinc fluoride, that's a metal and a non-metal. Let's see, zinc is one of those few transition metals that only makes one kind of cation, and fluoride is -1. So got to have 2 of these to balance out one of those. ZnF2. So if you look at the periodic table to see the average atomic mass of each one of these elements. If you look under lead, you would see 2.07.2. And so if you're talking about individual atoms, the unit is AMUs, atomic mass units. But if you're talking about molar mass, it's the very same number, but the units are grams per mole. And I can show you the math that makes that happen if you want to, or you can just take my word for it. So the molar mass is 207.2 grams per mole. Now, when you've got a column of numbers like this, you can put the units with each entry, or you can just put the units up at the top of the column, and then they apply to all of them. So O2, we've got the subscript 2 tells me we've got 2 of those guys. So it's 2 times the molar mass of oxygen, 15.999 is the number that you see below the symbol on the periodic table. And that's 31.998. And now that I've told you about this thing about the units at the top, I'm still going to do this just to make sure that we're connecting it with molar mass, and it's not tiny microscale where we want to know about what's the mass of one oxygen molecule, which would be 31.998 AMUs, or atomic mass units, which are teeny tiny in terms of grams. All right, so with zinc fluoride, we've got 1 zinc, so 1 of these, 65.409, plus 2 of the fluorines, which are 18.998. And if you add those all together, you get 103.405 grams per mole. And mole can be abbreviated MOL, but it's not much of an abbreviation because you just drop the E. It doesn't really shorten things up any. All right, so if you would, please answer the question at the end of this video and then come on back.